Leon, thank you for the introduction. My name is Brian Anthony, as Leon said, and today I'd like to share with you a little bit about our work in deep reinforcement learned control, or how we're making actionable data analytics in the smart factory. Learned control, what is it? In manufacturing, you have control signals and materials that are going into a machine. And that machine is taking material in and putting material out, the product, final product, or work in progress, and also generating a lot of data. Whether we're talking about making coffee that you're enjoying for your morning brew, whether it be a light roast or a dark roast or something in between, or you're making optical fiber or fiber for your clothing, which if you look at it in cross section has different mechanical, electrical, and optical properties. All of these products, coffee, fiber, additive manufacturing, there's a machine making a product. Those machines, here a coffee roaster, or a fiber extruding device, have data and control signals associated with it. Pressures and temperatures and gas flow as a function of time, force and velocity as a function of time. So what is machine learning? What does data analytics have to do with this? In the manufacturing environment, at the heart of maintaining quality and achieving a certain performance is real-time feedback control, where you have a set of things that you want to maintain, either their absolute controlled value over time as a steady state, or some value that's changing. And in the context of fiber, we are controlling the preform speed of the glass ingot that's being put into a furnace. We're controlling the furnace temperature. We're controlling the tension with which we're pulling the fiber, and we ultimately control the fiber diameter or other mechanical aspects of the fiber. For all of these things, for all of these parameters, all these settings, the general framework is we have some type of process. Before that process are control signals that drive that process. And those control signals are determined by a thing called a controller. And that controller takes as input, what is it that we want, our set point, what is it that we're getting, and making decisions based on either the error or the derivative of the error or the integral of the error between what we want and what we get. Now, many processes in the manufacturing environment use sort of very classical techniques, such as proportional integral derivative control, or slightly more complex techniques, such as state space modeling or linear quadratic control, or do a little bit of modeling of the physics. Now, in all of these scenarios, all of these sort of classical and heavily used control strategies, they're very much tuned and optimized to a particular and nominal set point. They work very well when we're trying to produce a particular roast of coffee, a particular color, or trying to achieve a particular nominal diameter of our optical fiber. It's very hard for these controllers in general to then be reconfigured rapidly and changed to operate at a new set point to produce fiber, say, with modulated diameter, or a larger diameter, or coffee with different tastes and colors. So it's hard on the factory floor to take these real-time feedback control systems and adjust them. It's hard to model the systems that they're controlling. It's hard to model fluid dynamics, heat and mass transfer, and vibration, except operating around the steady state of operation, which is where these control strategies work very well. Where we are innovating is learning to control dynamic processes that are otherwise hard to model in real time. The impact of our work is we fit into the existing control strategy of life. Time varying signals driving a machine, making a product, and we learn to control. We learn the physics of operation, we learn to optimize the process, we learn to make new variants of the process. In the context of machine learning, the architecture that we use is an agent, an action critic feedback loop, where our action is the controller, our environment is the manufacturing process, our state and reward is the sensor reading, and our agent is the controller. Putting a little bit more sort of context to that, a little more graphical, paying attention to the big picture here. We have a machine that has a product that is producing here the fiber. In this architecture of this actor-critic approach, If we drill into the actor is nothing more than our control system. The actor is your conventional feedback controller where you have a system here, the extruder, the spool, the plant that's doing the thermal heating of the fiber, and we have the thing called the DRL agent, the deep reinforcement agent, that is controlling in real time. But sitting on top of that is all of the additional machine learning infrastructure that you would typically do offline. As we're doing the real-time control, we record our history of data. And as we observe that history, we steadily learn about the physics, we steadily learn about the process. So as we're learning, instead of taking our data and then doing an offline batch sort of interpretation of the data, we learn about it in real time, we update it in real time, so that we have simultaneously the real-time learning, the real-time control, that allows us to be more innovative in how we perform control of fiber production or coffee production. The graph here is just showing that over time, if we tell the system no prior knowledge about how it operates, it can, with different learning rates, get back to a performance level that exceeds what a classical PID controller can do for us. The experiments here, a little bit on fiber. What's really interesting here is the summary that our deep reinforcement learning approach is beating the benchmarks of PI, PID, and other classical control strategies. But if you think of fiber extruding for a second, it's a material in and material out. It's a mass flow problem. And our learning approach learned here how to simultaneously push and pull the material that's coming out and the material that's going in to very rapidly respond to step change command inputs on modulating the fiber diameter. So the system that we've developed, it's a control strategy that doesn't require analytical or numerical models to start, but it learns them. It can predictably, after learning those models, predict what new control strategies should be put in place to optimize performance. We're able to implement this in real time. It uses the reinforcement learning, the deep reinforcement learning architecture, but at the edge and in real time. We've deployed it on a fiber drawing system and in progress in coffee roasting. And we look forward to applying this to other areas, other processes, other manufacturing processes that are difficult to track and hard to model. I thank you for your attention and want to also recognize the graduate students that have been heavily involved, both Songwoon Kim and David Kim, and welcome your questions on deep reinforcement learned control.